So to conclude things for today, we were a little bit ahead of schedule, so we caught David off guard just a bit, but he is here now. We wanted to tie things up with the partnership work that DDN and SGI are doing around some of the very large models in the weather community. So David, thank you very much for joining us, and sorry to race you in at the last second.
All right. Well, thanks for the invitation to come speak here. I may have too many slides for 20 minutes, but I'll try to run through it a little faster, but some of it. How do I advance it here? Oh, here, yeah. I'm a Mac user. So what I'd like to talk is just briefly about first my position at SGI is to do the business development marketing side for weather and climate air sciences centers. I just noticed the last few minutes on the previous talk, and I don't know what was the whole topic, but I saw some chart from Running Wharf, so that's in that area. And tell you a little bit about what SGI is doing in that segment and our connection with DDN. Oops, wrong one. So first, we established kind of certain verticals, and you see weather is one of the places which we find decided to have particular focus on as of about a year ago. The SGI had some presence in the segment, but we didn't have an active marketing activity on that. There is here a quote from iCheck, the Irish Met, about the SGI system they have and the good things it did for them. I don't know, is the plan is to distribute the slides afterwards? DDN people? Nobody knows? Okay. A little bit about the landscape. What typifies the segment? And by the way, so there are several users here. I don't know if there's any users from the area of weather and climate here? From any organization that relates to it? No? You're all from another areas. Okay. So it'll be a little tutorial. Okay. What's typical? First, there is kind of weather forecasting and there's climate research. And they're very different operational requirements. One is mission critical, and you need to have reliability and be on time and 100% availability. The other one is a more researchy. So it needs to be more flexible in configuration and so on. Almost every country's got a weather center. There is a lot of international cooperation in the field. People share models and information and certainly observation data. So there is a lot of collaboration going amongst the customers in weather and climate. They also have a big impact on us. So one of the areas where it's not so difficult for people to get funding for, because we can measure the impact of doing a better precise forecasting on how much it saves for the economy if we know where a storm coming and when and can prepare for it. It's much harder to explain to people why tax dollars should come to, say, explore black holes in the universe. It's a little, doesn't have a daily impact on us. I mentioned that as weather and climate, and if I had a much longer time, I'll go through this. What's the difference between weather and climate? You know, one of the things is people saying, well, we cannot predict the weather accurately for tomorrow. What's the point in running the models and tell us what the climate's going to be 50 years from now? Of course, there is an answer to that because we're not measuring the same quantities and so on, but a lot of people are, in particular, when the politics comes into it and the skeptics trying to find arguments against dealing with climate impact, they use this kind of performance. There are good answers to that for the community. I think I mentioned here the items here, the difference, though both weather and climate run very similar models. What they measure, the quantities they're trying to accumulate are a little different in nature, but the numerics and the computations are sometimes use the same model, either to do forecasting or also for climate, such as the unified model in the UK Met Office. But the operational environment, the facilities requirements are different. A little bit about what a workflow looks like for weather forecasting. First, there is the phase of collecting data. It comes from different sources, and that's a big problem because you have satellite data, you have different formats and different accuracy and different distribution of collected data from ships and airplanes and ground stations and satellites and various things that collect the data, and all comes into the input, and it needs to be processed quickly so that you have very accurate initial conditions when you start doing the daily forecast. So that's the stage of the data assimilation, where you do analysis and prepare the initial conditions of the model, after which we run the model. And then there is the phase of post-processing. You get raw numbers from the model. You need to somehow make sense of all the numbers there. So you create charts and maps of the temperatures, the winds, and over time, if the forecast is, say, for the next 3 days, then you create it over time. And that information is now taken by the people who deliver the forecast. And here there is some subjective judgment that comes into play. The people who you see on the television look at the output from the models, the post-processing, which is just charts and numbers, and trying to make a prediction about probability of rain in a particular location, for example. So most of us here are dealing with the phases of data assimilation, running the model, and post-processing. That's where compute servers and storage processing comes into, plays a role. So those 3 areas in the center, on the right-hand side, is where our equipment comes in. There are some challenges in that, in the model, and it's very computational intensive. It's one of the areas which uses the most cycles in various research institutes, academic universities. That in life science are probably equal in size in terms of the bigger cycle consumers. Because when you're trying to get more accurate weather, you can imagine that you map the Earth into a grid, 3-dimensional grid. And the tighter the grid is, the higher resolution, the more accurate the forecast is, as you can intuitively gather. When we're trying to reduce the distance between grid points by 2, the amount of computations we add is about a factor of 10. There's 3 dimensions, and there is a time step that needs to be doubled as well, or halved in size. So you get about 10 times more computation. So it's very compute intensive, and it produces that much more data as well. So there is a lot of challenges here in the resolution. There is more complexity, put more physical and chemical processors now. The models now try to measure air quality. So you need to have a very fine phenomena of what happens when the gas are emitted into the atmosphere. And of course, the other things I forgot to mention, when you do climate, when you do weather forecast, we're just dealing with the atmosphere and the surface of the ocean. And that's sufficient, because the surface of the ocean doesn't change too much over a period of 2 or 3 days or 10 days. When you do climate, we need to simulate the ocean all the way to the depth of the ocean and under the surface, because turning of the water of the ocean is one of the big factors in changing the climate. You probably all heard about the El Nino. El Nino is when warm water comes up to the surface and it produces a lot more moisture, and we get much wetter winter in places like western US. And various other things that add more computations. Now, there is also the question of data in that. So there is a lot of data. Data comes, the 2 huge amount of sources of data. One is the observation data. When you deal with satellite data, it's a very large amount of data. And that's data that you typically need to run the models, and you use it once and it's done. But when you run also climate modeling, you can produce a huge amount of data, depending how much of it you want to save as you simulate. If you simulate the next 50 years, and you go by time steps of 30 seconds or 1 minute, you can imagine that there is a lot of data that you can save. It's also important to save the data because people question results of climate simulation. You need to verify it. You need to have other teams who can repeat the experimentation or simulation that you do. So there is a lot of, there's a need for a lot of data. You can see here in the case of NCAR that they have 50 petabytes of archive. Just for the last 50 years, they saved 10 petabytes of historical data. The rest of it is kind of computed data, simulated data that's used for research. On a post-processing top, that's another computational need, a little different. You want large memory, and that's something actually that may play in other scenarios too, in other industries. When you have large amount of data that you need to analyze, there's a lot of talk about data analytics these days. There is a lot of benefit of being able to access the data quickly, not having it on rotating disk. So now we get into DDN has some products for that, IME. SGI has got a shared memory system where you can put lots of actual memory. And so different levels of memory between memory and non-volatile flash, and then disk, and then tapes. The hierarchy of it and how you organize the data can make for a more efficient access when you need to analyze and study data. We find, talking about the data, I find that there is good synergy between what DDN does and SGI. So we actually have frequent conversation about working together with several places. We use DDN. I'll talk about NCAR in a minute, and in the UK Met Office, there is DDN equipment in other places. What we need data for weather climate requires a very high performance parallel file system and be able to distribute it along many I/O channels. So we find that between SGI and DDN, we are kind of establishing good working relationship in various areas. A little bit about our customers. How much time do I have? I got 15 more minutes or so? 10 minutes? Okay. So I'll tell you a little bit about NCAR. This is one, for us, is a very big research site in the weather area. The announcement was early in the year, in January, that SGI has won the compute system and DDN won the storage part. So together, it's a very impressive system. It will be used to mostly for developing models that will help other agencies deal with the impact of climate change. That's a big part of what they're doing. It includes also air quality and wildfires and flood predictions and so on. So many different types of models. Now, NCAR does not produce the forecast or the prediction on all of that, but it develops the models that the other agencies will be using. What the system looks like, it'll have a 5.3 petaflop system, the SGI ICE XA, which is our high-performance cluster, tightly coupled, with 28 racks. You can see that the system has 145,000 cores in it with the newest Intel processor, the codename Broadwell, and large amount of memory, over 300 terabytes, using also the most recent high-speed memory system. Now, some of the nodes are with 64 gigabytes, some are with 128, 20% of them FATR nodes. We're using InfiniBand EDR for that system, so the new generation of InfiniBand. On the side there in the table, I put together what DDN has put there for storage. It's configured for 20 petabytes, so it's a very large storage system with the SFA 14KX systems. It's also expandable to 40, so there is an option or the potential of doubling the storage size. It's very a good performance I/O system at 20 gigabytes per second aggregate on that, and you can see the drives it uses. The choice of GPFS is NCAR's choice. So GPFS is popular with weather centers. It's a high performance. It's an IBM file system. It's high performance and parallel system, and NCAR has used it in the past, and they like to use it. But there is, as I mentioned before, there is between Luster and GPFS, we see about equal requirement in that segment. One of the things that we're constructing now, and it's part of the contract between SGI and NCAR, is a joint center of excellence. So we'll put some people from SGI and some from NCAR, and we'll work on some performance of applications, but mostly around the system level. So scaling applications, libraries, and the system tools that requires for that, and also partly of looking at future architectures. And that includes looking at various ways of doing I/O and storage and connecting the post-processing and speeding up the whole workflow of climate research data, as well as experimenting with algorithm for the interconnect to do parallel programming more efficiently. If I didn't mention before, and unlike the typical cluster will have a fat tree InfiniBand topology, our system is built with Hypercube. In fact, enhanced Hypercube, because there's some extra links there. But it's a multidimensional Hypercube, which has a different properties. It's got its plus and minuses relative to fat tree, but it's a more, one of the big advantages it is that it's easy to upgrade system without taking the whole system down. I mean, you can deal with a part of a Hypercube. You cannot do it with fat tree. Fat tree, whenever you touch the whole, you don't know what else you're touching because there is a multiple distances of the connections. So it's also useful when you have near neighbors, finite people who know numerical analysis. When you do finite differences and you deal with nearest neighbors, Hypercube is a more natural topology. In any event, this joint set of excellence will also plan to hopefully bring into some projects some of our technology partners, such as DDN and Intel and Mellanox for the interconnect, as well as possibly some other end users. So we can work on system levels, issues of parallelism and scaling at the high level. Some of the things that the system at NCAR is called Cheyenne. It's actually located in the city of Cheyenne, Wyoming. It's just about, 50 miles north of Boulder, where NCAR is, Boulder, Colorado. So one of the things they're doing is the stream flow I mentioned before is to predict floods so people can plan for reservoir catching water and also damage from floods, severe weather, which requires very fine resolution of models, looking at solar energy. People talk about renewable energy, and a big issue of solar energy is trying to predict the cloud cover as to what we can expect in production of solar panels so that they can be supplemented from the grid, from the power grid when necessary. Get more accurate regional climate change. Just to say that, the whole western US is going to be dry or not is a little too rough an estimate. So you're trying to get more localized information on the prediction of climate models so you can plan, when you plan for the future, even plan what crops should be going in these things. This kind of things is going to change. Where we go today, particular plants or crops may not be the same 50 years from now because of change in the weather patterns that happen because of climate change. And various other things that will come in. At the bottom line, you see one interesting thing, they're also not looking at some of the atmosphere outside of the Earth, in this case the sun, and trying to simulate or do modeling of solar storms. So now that's important, even though it happens on the sun. It's important because when you have these magnetic storms on the sun, it affects our communication, satellite communication. So it has some impacts on our daily communication when it happens every now and again. There's a cycle to it, and there's some predictability. Just some list of SGI customers in the weather area. In this case, it's Europe and the Middle East and Africa. I'm listing here some of the national centers in some countries where we are present on operational weather forecasting and some in oceanography. There's some research institute. I won't spend too much time on it. There's a list of of customers. Some of them are renewing the systems and some new coming in. This is some list of some of the Asia and Australia. So we have systems in Australia, in Korea, in China, in Japan. What else do I have here? Malaysia, Bangladesh, Malaysia, and such. So that's quite a bit of presence. And in the States, I've mentioned NCAR, but you also have some equipment, big clusters in NOAA, in a big system at NASA. Did I miss NASA? Oh, yeah, I do have under climate, NASA Goddard. We have a couple of, about 3+ petaflops of computing at NASA Goddard. We're doing climate research. And several systems in Brazil, in this case, Brazil and Peru. So this is kind of the customers we have. Now, what SGI doing in that area also, which is important, is investing in weather models. We figure that this is an area where you need to be competitive. You need to spend time on optimizing models, and you cannot just do it when you get the code to, the sites when they try to buy a system, say, give us a benchmark and run it. You need to really understand the workflow and spend more time on optimizing. Otherwise, you cannot do a good job on it in 4 or 6 weeks. So we want to track some of the important models. Fortunately, and we created a kind of a global virtual team for that. People have experienced before in weather models and getting more now, and we added some people. We have about 6 to 8 people who have very good experience with some of the models, and we're using them in our kind of pre-sales and application support. Fortunately, when you take the main models in the world, and I'm listing some of them here, a group of in this case, I have here, 8 or so, and different types. Some of them are atmospheric models, climate, ocean models, and data simulation codes. When you look at these things, it covers big part of the global market because there is a sharing of information. The top one, WRF, is used in hundreds of places around the world, and we see it in benchmark. Many places, universities, academics, and other research places running WRF. It's used both for forecasting and for climate and various other things. For chemical, there's various flavors of WRF for different purposes. And then there is a CSM, is a climate model. Now, climate has to have multiple components. So as I mentioned, there is the atmosphere, there is an ocean, and there is the ice land, and there is ice on the sea, and then there is a coupler to get them all together. One of the challenges of the climate model that in atmosphere, things change a lot faster than they do, say, in the ocean. So when you do numerical simulation, the time step you take doesn't have to be the same. It needs to be smaller in atmosphere than it is in the ocean because things change slower there. So the coupling is an interesting programming challenge. So we have that. We're using the unified model from the UK. In Germany, they've developed the Cosmo, which is also used in some 8 to 10 countries. And then they are actually moving to a new model called ICON. ECMWF, the big center in the UK, has its own model. IFS and the next line, Harmony or Rome, are the same family of models. So they have some commonality, which helps in developing it. Fordivar is a data simulation. There is a new code that being developed that might replace WRF in few years called EMPAS. So we start looking at that. ROMS and NEMO are ocean models, also very pretty popular ocean models. I don't list here some other codes that people tend to use that are being used less and less. There is MAM and POP, and there are some other codes that have been popular 10 years ago and not so much now. And so I won't list this. So these are the major codes that we are working on it. And I will just finish here, so I will not go into details here, but I just want it's one of the things that we feel SGI is strong in. I'm from SGI, so I'll do my little marketing here. The areas which are important in the areas for weather and climate are application knowledge, and I put it at the top of the list here. The other thing is our products are energy efficient. So we have some, when you look at the Green 500 and you take away the system that use accelerators, then SGI systems become the top system in energy efficient. It's significant for this segment because there is now one example of a center that uses accelerators, but most of the world does not use accelerators for weather models. It's very difficult to make it good, efficient use of them at this point. We'll see what will happen in a few years. The one center that uses the Swiss met, at least they demonstrated that they can move the whole code, and they use Cosmo on GPUs. We have many features that can add to the resiliency and high availability. They are both monitoring the system constantly and being able to do some redundancy in components that add to the availability of the system. Live integration is the things that I mentioned before, the ability to upgrade part of the system or fix a bad component without taking the system down. To an operational center and even research center, it's very important to, when you want to upgrade or put some of the system, the next generation processor, add more memory, or fix a broken node on that system. If you have to take the whole system down, then you lose millions of core hours. If you can do it just with a small piece that's broken, without disrupting the operation, it's a huge win for the facility. So we find that more and more people value that feature. And we have a very good world-class services on that. So I think, well, I have another one here, but I can briefly, some of the list of why our products are suitable for the weather segment. But I will stop here.